We are not hitting at all, the targets that we need to, keep the warming controlled. This is absolutely needed to enable more electrification, and more electrification is the way to decarbonize. To me, there is nothing else that's the most important.
Decarbonizing the power sector attracts most of the energy transition's attention. While replacing fossil fuels with clean energy is a critical step to combating climate change, it only addresses a piece of the challenge. Modernizing the power grid from interconnected poles and wires to an intelligent and dynamic machine is paramount to meeting the moment. The digital grid is coming, and just in time. Utilities in the US are still in the early stages of realizing this opportunity, but change is coming swiftly, and their European counterparts have created a blueprint for what that could look like. I'm John Engel, Editor-in-Chief of Factor This. This episode, I'm joined by Arnaud Cantin, Senior Vice President of Digital Power at Schneider Electric. Cantin shares why a smart grid, not only clean power, is crucial for the energy transition. Why do we need it? What could it do? And what's stopping us? That's all next on Factor This. Arnaud Cantin, thanks so much for joining the Factor This podcast. It's great to see you.
Great to see you too, John, and happy to be with you for the podcast today.
Yes, and I think this will be a really good conversation for a couple of different reasons. Obviously, resiliency and reliability are top of mind for utilities and really anyone with their eyes on the energy industry. But I'm excited to dive a little bit deeper into what's happening at the substation level and this transformation into what we call the smart grid as an industry, but it means so many different things to different people. And I think at times can get a bit ambiguous as well when we don't add some depth into what we're actually talking about when the grid gets smarter. So before we get into all that, Arnaud, please do take a second to introduce yourself to our audience and lay out a bit what you're working on over at Schneider Electric.
Sure. So I'm leading what we call our digital power business, which is essentially all the digitization layer we put above electrical systems. So it's a combination of electronic devices like production relays, metering, and so on, tied together with software to manage, in particular in the utility world, all the substation level. We have a different division doing the centralized software like ADMS. But also on the demand side for our demand side customers, all the software layer managing the facilities from a power management perspective.
And I think you will be very helpful in giving us a comprehensive view of like what's actually going on in the market, because as astute listeners to this podcast will know, Schneider Electric has its hands in just about every cookie pot when it comes to the grid and energy, whether by name with the masthead of Schneider Electric or through a subsidiary or an investment or something. You don't have to dig for very long with some of the major players to find a link to Schneider Electric. So I'm really excited to dive into all that with you. So let's start off then with the premise for this episode and how I kind of introduced you and set this up. What do you think of when you're talking about the digital or the smart grid, and why is that so critical to the energy transition? Even people who maybe not directly associated with grid operations or utilities, why is the smart grid important for all of the ambitions we have around decarbonization and reliability and so on?
Yeah, I think there are definitely many different aspects in attributes of a smart grid, but in a condensed version, in my view, it would be really a flexible grid which can accommodate a fast increasing number of distributed energy resources and variable loads like EV charging, right? And while maintaining a very, very high power availability, really striking that balance of maintaining availability but creating flexibility on the other end. Maybe I also tie it to a time factor in a way. Maybe I'd say a smart grid is a much less rigid grid than what we have traditionally, where the cycles of evolutions in fact can be shortened a lot to reduce the gap between that, very slow moving infrastructure, traditionally, and the required speed of evolution of our energy systems to support the much needed decarbonization.
So what does the current grid look like then, or the dumb grid? I don't know that anyone actually calls it that, but whatever came before this vision of a smart grid, how does that look, and maybe what are some of the pain points there in why we need to evolve and become more digital and take better advantage of the data that maybe we already have sitting out there too?
Yeah, as everybody knows, it's first a unidirectional grid, right? So it's, top down, big power plants generating power, getting distributed to loads, and, every consumer just receiving electricity. So, that's what we inherit. And that's a very rigid infrastructure, which works well when, things don't evolve that fast. And that's what we've been living with for more than 100 years. So that's a rigid infrastructure. That's an aging infrastructure as well, right? We see that, it's been built, especially I would say in the US, nearly 100 years ago. And, we still have very, very old, you could not imagine the type of equipment we still see in the grids. And so it's a very aging infrastructure as well. It's also obviously a grid which is not made for variable dynamic power flows. So there's a certain idea of stability with inertia usually in the grid, meaning that the time constants are relatively long, so the time to react can be doesn't need to be that fast. That's not true anymore, right? So renewable generation is variable, is based on power electronics, which, has very high speed reaction, but no inertia. And so, this existing grids, from that perspective, don't really allow, to have this kind of variable generation and loads that are necessary to decarbonize and make the world a better world. I'd probably add to that as well that, the reliability itself, which used to be maybe, quite a large attribute of what the grid was trying to achieve as a main target itself is at risk, right? With all the, known weather events and increasing weather events. We see that in reality, and we've done a lot of analysis with some of our customers, the way the grids are being protected, for instance, doesn't allow to avoid those kind of events. So it's still, what is truly installed compared to what the technology enables today is really of, I'd call it middle ages of the grid, which means the reality that, the number of schemes that would be necessary to avoid those events and all these wildfires, for instance, that are actually just not existing, not configured properly, so just not operational at all.
And what's interesting in having this conversation too is a lot of those challenges that you just laid out aren't necessarily new. Like we're more than a decade past, when variable generation started to flood into the market. Transportation electrification in both Europe and North America is, out of the gates and moving pretty quickly. So we've spent some years now knowing that the grid is changing and that we need to be more nimble and we need to be more flexible. But it almost sounds like we're arriving at some kind of juncture where you either innovate or you're going to really be caught in a precarious position if you're a grid operator or utility, so on. So what is then standing in the way of a utility really taking advantage of the digital grid and investing in that space? And I guess the follow-on question to whatever your response is why haven't some of them done it yet?
Mm-hmm. Yeah, first to your comment on your initial sharing. Indeed, I think one of the biggest challenges that's being faced is that the proportion of renewable generation has increased massively now. So it's used to be a very small portion which doesn't impact a lot. Now it's a much bigger one. And the traditional response, in fact, to those changes has been your investment in grids, so laying out new lines, increasing capacity, generally speaking, of the grid as a whole. That's always very, very long and complex projects, right? It's taking a lot of time. So what's changed now is acceleration of installation of the variable sources of generation and loads, while at the same time, the time to develop the grid remains the same. You still need to put poles and cables and pretty heavy construction, or dig the roads to install new cables in the city and urban environments. So what's to your question, I think what is really needed and where solution can be found in the short term, because there's still a needed investment in capacity for sure, is how the digital solutions can help create flexibility, so that with a given hosting capacity of the grid, we can increase this variability and these power exchanges, bidirectional exchanges, better balance at every level of the grid. Not only, let's say, at the top level, high voltage and interconnection of systems, but down to the low voltage grid management, where you have more and more local generators, storage capabilities, and variable loads. Optimize at every level of the grid, from the top to the bottom, the exchange of power flows, the exchange of energy, so that you maximize, in fact, the utilization of the existing assets of the grid, so that it gives you the time to also, increase that capacity.
And, the book on utilities over those years that I described too is that they're, resistant to change, and they don't want to evolve. They don't want to embrace technology. And I think maybe to a degree that was true. But I feel like at least where we are now as an industry, I mean, I'm talking to utilities every single day, and obviously we operate Distributech. So this is where utilities go. They want these answers. Like, they're looking for them. It's not that they're avoiding the challenge, at least anymore. Is that your sense too? Is that the market has shifted a bit to acknowledge these are our circumstances. We have to do something about them, but we want to make sure that we're, prioritizing the right investments and, joining with the right technology providers. We always joke that no utility wants to be a first mover, but they'll be a really fast second, first follower. So
I think there is a combination of different factors here, but the first thing I'd say is I don't believe utilities are not innovative companies. The cycles of innovation are very long indeed. And that's the point, right? So yes, there is some risk aversity for a good reason, that, the main target remains the reliability of the power supply to the consumers, right? And that's what they are living for. And that doesn't change. So that maybe the cycle time of innovation has been traditionally very, very long for that very reason. And so I don't think it's because companies don't want to innovate. It's just that, from the time that you start innovating to the time it actually hits the grid in the real operation, those cycle times can be very, very long. Typical maybe 20-year cycle, right? So that's indeed very long, but for a good reason. There's a good reason behind that. And seeing what we are facing now, and the main change we are seeing is that those time constant need to reduce. That's the only way to be able to solve the new equation that we're facing collectively. And that's why I think the change of mindset is also coming from these power distribution companies, that help us out, accelerate that, because we cannot jeopardize, but at the same time we know we need to accelerate. So how do we do that, right? So that's where I would see is a major challenge there. So not reluctant to innovating or to change. I think it's just a question of how we accelerate the cycle. That's because of climate change impacts, and so that frequency of extreme weather events does increase, and we need to tackle that. That because also the development of technology is going faster and faster. So being able to adopt faster the new technology will help solve some of these issues. There is also a challenge for utility companies in the aging workforce, retiring workforce, young people that don't necessarily want to get in there. So how do we, better manage the expertise from inside the head of a couple of people to more into systems and artificial intelligence and support systems in general, so that expertise can remain centralized, doesn't need to be everywhere available to be able to operate and manage the upgrades. So I think there are a number of factors there which creates really a problem space, which is really for me around time acceleration.
Well, I think we can solve part of the workforce challenge if Schneider would stop hiring all the best engineers. I know the utility.
I can tell you, Schneider Electric is struggling like every other company to find the necessary workforce for the deployment. So a lot of our own investment within the company is to how we better empower our own workforce, especially for the field services. And I think it's a very common, common theme with it's not only utility companies. We face the exact same problem of labor shortages, but not only about capacity. It's also about, how we deploy faster the competency. So, a lot of investment actually is also going into, making our workforce creating an easier way to train them, to deploy the competencies in the field and provide more and more remote and centralized support, so that you still need the expertise, you still need human beings behind that. But how do you make it effective that maybe you can support a pool of 1,000 service engineers with 3 or 4 experts that are connected with the right digital tools to enable the local guys who are in the field to do the right thing in a better time frame.
Yeah, and I'm obviously joking, but it is about doing more with less. And I know Schneider's doing a lot with AI to help utilities, expand that reach and get more done with the people that they have and the expertise that they have, and taking some of that off their plate. My last question on the innovation cycle, because I'm really glad you brought that up. I wonder if that's something that's a bit different with the digital grid, smart grid conversation, because we are talking a lot about software as a service and the speed at which you can move as a software provider to update that or patch that offering for a utility, or expand in building blocks. I'll call out one of your customers. I know you've done a lot of work with PG&E, and how that relationship has blossomed over the years into ADMS and a number of different things. You can do that in iterations in a way that with big hardware can sometimes be difficult. I don't know if I'm comparing that appropriately, but I think about utilities always being fearful of stranded assets and lead times for, when you're dealing with transformers or anything big and, physical. It's much tougher to move quickly. And then I'll see an RFP for an ADMS or a DERMS or a digital substation software package, and they want it delivered in 18 months or 2 years. Like, that's pretty quick.
It is indeed. And I think that's, where we are heading towards, in fact, is how we can maybe dumb down actually the equipment so that it's really standard. You have a fixed infrastructure, fixed rating, fixed even IT infrastructure inside a substation, and then you can play with software to evolve, because what we need today and what we know of today is such, and tomorrow we know we need other things. We don't know what they are yet. And so that's really about creating that flexibility, so that as much as you can, the physical infrastructure, including what is hosting the intelligence, can stay, as stable as possible. But then you put the smart in software, so that you have, the facility of, easily managing and deploying, upgrading those applications, from remote central places. You don't have a truck roll every time you want to do a change into a substation. And that's where, when we talk about, virtualized, substations, there is virtualized protection, automation, control system of substations. So it's really about distributing the intelligence between the central location and the local edge level, substation level, because you need to have some local optimization schemes to be able to optimize those energy flows. It cannot be just a big central computing machine that has sensors everywhere, data from the whole grid. Practically, that doesn't work. It does bring a lot of value for sure, and we put a lot of efforts, obviously, in the central grid management systems. But I think what we've seen as a movement in the past 10 years was really about this kind of big data, concentrate everything, put a big brain in the middle. I think we are, moving a bit further along, saying, no, you need those big central brains for sure, and they have a lot of value and bring more and more value. And at the same time, you need to bring intelligence at the edge level, at every level of the grid, because of latency, because of local optimization you want to handle. And it's not practical to try to have, too much concentration of the intelligence in a central control room.
So you've used the word flexibility a couple of times now, and I know that Schneider has been, laying the groundwork on this concept of flexibility, and what the digital grid enables is flexibility in a dynamic system. We're hearing that word flexible and flexibility a whole lot more now with this change in conversation around data centers and large load customers trying to link to the grid, and the value that a utility can realize by digitizing its existing infrastructure, especially at the substation level, to deal with the demands of these massive projects. And again, saying Schneider is involved in so many different businesses, I know you serve the data center side as well as the utility side, so you guys really see this picture clearly. But how do you think about the imperative of utilities taking advantage of what they've got, making the investments to still allow them to onboard new customers and get the most out of what they have, even acknowledging that infrastructure is always, new infrastructure is always going to be a piece here. But flexibility seems to be, the word of the year when it comes to utilities and load growth and data centers. And you guys have been talking about this for years with the digital substation conversation, but it seems that it's got new weight. Would you agree with that?
Yeah, definitely. I think it's becoming maybe the central theme as we speak, because of it's also yes, very very large loads like data centers, and at the same time a lot of distributed smaller things. So it's really at every level, and indeed we have the chance of working with both the supply side and the demand side and every type of customers. So we see how our different type of customers view the other side of the grid and the equation. So when you put yourself in the shoes of the data center customers, more and more of the request is around decarbonization first, right? So it's how you can supply and maximize the amount of green energy, in fact, that is supplied into a data centers, because there is very less flexibility on the load side, obviously, because there need to be also available IT services. So we don't play that much on the load side. We can put, to some level, some local resources as well. And the number of customers are starting to do that. So we need to play between, let's say, off-site resources and on-site resources and optimize with that. So we see, and then you need to manage a fleet, right? Fleet of data centers, but also a fleet of, renewable sources which are contracted through PPAs. I think the big evolution we are seeing is actually the optimization going into more of a real-time optimization. So no more buy a lot of energy through PPAs, and in average it works, but the reality of the electrons being consumed is quite different. We are moving out of that, which is okay. Now we need to look at optimizing on a 15-minute basis every time, based on forecast, what's available from the grid, what is the CO2 intensity factor, right, of what you source. Do you have dedicated, renewables attached to your site or through a developer that or an IPP that's selling you that energy? But how do you make that optimization in real time? So that's, I would say, more and more what we see is on the demand side type of optimization. But that also assumes that the grid itself is able to bring those different flows of energy into the data center. And so I think we are seeing more and more discussions actually between the supply side and the demand side from that perspective, with utility customers also trying to make sure that their highway of electricity is enabling to arrange those flows, which are also variable, but at, call it maybe a macro grid scale. No more just a local site. So we get out of the notion of one site to optimize to a fleet of sites which is distributed over a grid with a fleet of generators that's distributed as well, and trying to make the best balance to decarbonize as far as possible the power, the energy supply, into the facilities.
So we know that utilities recognize the value of data. There's this big push in digital transformation to digitize really their entire operation, from what, decades ago was logging on, a notebook, and grid operators would just kind of keep those notes to themselves, pick up the phone and call another grid operator and exchange data points. And, we're feeling the pain a little bit from that analog world as we've now evolved, and we don't have great visibility into the assets that are actually on the grid, and we don't always know how consumers are behaving at certain points of the day. And technology is enabling all of that, and I think we spend a lot of time on distributed intelligence and smart metering and DERMS and ADMS, and you get into all these different applications. But why is the virtual substation, the digital substation, so important to this mix? And maybe it's even helpful to provide a little bit of a definition on, what we're even talking about when we talk about digital substations.
Sure. And indeed, I think it's one of the key elements beyond many others, for sure, because that's a whole system that needs to be managed. But I think that's one of the key missing elements actually today in the equation. So the way I would characterize, I think I like to move from the notion of digital, because it's already digitized to a certain extent. So, you convert maybe analog to digital, you gather data, you're connected to a central ADMS, or as a minimum as a SCADA for the operation of the grid, depending on the size and of the customers and how much they could invest. So it's digital to a certain extent. But I think the next step that we are considering, and that's really in light of the flexibility we discussed, is virtualized substation. And so what's the difference? So it's the next step. That's obviously still digital, but it's really to abstract the physical layer, which are equipment, which are actuators, switchgear, transformers, and so on, and sensors which are necessary to get any information from this equipment and from the grid itself, what's happening in the cables, what's coming in and out. So that is physical by definition. How we can abstract ourselves from those so that infrastructure becomes fixed. And then the whole intelligence that is located in the substation, so the protection algorithms, the automation, the metering that we put into substations, is becoming a software that is running in a computer. Right, and that's the difference. So instead of running those algorithms in complex, pretty closed firmware in electronic devices, which are dedicated each box to a function with pretty closed, highly standardized, regulated type of thing, move the intelligence into a computer at the substation level. So that's what we are talking about. What difference does it make? In fact, it makes a big difference in many aspects. So the first thing is in the construction itself, in the sense that it's simplifying a lot the equipment. So not having the intelligence embedded from a pure supply chain perspective inside the equipment makes it much easier, because the equipment becomes maybe less smart actually, because the smarts are above, right? And that can enable to simplify a lot, so the deployments in the field. The fact of virtualizing also means that the protection, automation, metering function that are normally run in those boxes are run in an IT environment, which means you will run them in the field in the exact same way you can run them in your engineering office much earlier into the project. And doing this early testing on those configuration and so on enables to do everything offline, upstream, test things, de-risk things, de-risk project, de-risk site interventions, de-risk commissioning, because the same software that we run on the site is a digital twin of this protection and automation system. So with this digital twin, you can test much earlier during the design phase instead of testing most of the things actually during the commissioning phase when you're under major time pressure because it's a shutdown, there's either customers not served or your reliability of the grid is decreased because, that substation is unavailable during that time. So you remove all that risk, you remove the need, the length of the downtime you have to upgrade a substation on the grid. So that's for the project side. But then when we move to the operation, obviously, then that's where you create a huge amount of flexibility. You can manage updates like a computer. You can upgrade applications like on a smartphone. Today, just to give you an illustration, just to change a protection scheme and upgrade a relay in a substation means one truck roll to the substation, means a full isolation of the substation because you're in medium or high voltage. It's a very hazardous environment, so you have to isolate completely before the worker is able to access the electronic components inside the substation. Then you do your upgrade, you recommission, you test, and so on. It's taking a long time for the operation itself to happen, but even the bigger time is the truck roll to the substation. So now in a virtualized substation environment, what we are saying is, okay, now you can also centralize completely the maintenance and the upgrades of a fleet of substations. So suddenly you're making that much easier to deal with. The expert that will configure has the tools to do it remotely, to test remotely and offline. Once you're ready, the deployment of these changes is like a computer upgrade. You load the image in parallel. At some point, say, okay, do you want to restart? Yes. We'll take a couple of minutes to reboot, and off you go. You've added, upgraded the application. You've added new applications, and I think that's the essential element, which, okay, today I have a certain set of functions that I need. Tomorrow I want to deploy something new because I'm adding new renewables into that line. I'm adding new variable loads. I can definitely, do that in a very effective manner without going to the substation. And that's a major change because then you reduce the cycle time and you make it very effective. You can manage fleets instead of doing each and every upgrade one by one in the field.
I think we've seen that throughout the utility business model too, the shift from cycle-based maintenance to need-based or condition-based, so that you're really making informed decisions about where you're doing the work and the resources you're deploying instead of just cutting trees every 5 years because you haven't done it in 5 years. And you see a lot of savings there. Quick aside, are you able to digitize and create this virtual substation for existing infrastructure in addition to new build?
Yes, that's what we are striving for. Comes with some constraints, but there are always ways to do it. And actually, to be smart in doing it, when you do brownfield, because most of the grid is installed and is there, so most of the interventions are in existing substations, which means the smart way of doing it is really to leverage the existing infrastructure of sensing that is existing in substations and plug the computer, if I may say so, on top of it. Right. So if you were doing a greenfield, it would be much cheaper then because you just instrument and then it goes straight to digital. Okay, you put your computers there, it's done. Here we are thinking about, okay, just keep the analog sensor infrastructure as existing. You don't need to rip everything, replace. No, just use what is available as long as it's viable inside the substation. Maybe when you go, add a bit of instrumentation where it may make sense, and then connect all of that, let's say a brownfield sensor infrastructure into a box that will be able to acquire those signals, and then you run your brains. So you remove the brains from the existing boxes; they become dumb boxes, and you just shift your applications to the computer so that you can manage it like a computer with the advantages I mentioned before.
I mentioned in the setup for this episode too that the U.S. is looking to Europe for a lot of these innovations and testing around smart grid and different techniques that utilities are utilizing to be more dynamic and keep up with that changing customer base and become more reliable, integrate more renewables. Any real world examples or case studies that we can call out around virtual substations? And is it in the field yet? What are we learning? Anything like that?
Yeah, I think so there are some, let's say, very early deployments still at this stage. So, for instance, what we've done is some field test of secondary substations, because obviously there is less complexity and less criticality in those, let's say, lower levels of the grid. So we have a couple of field tests going on there. So it's still early, let's say, very early deployments, but it starts really hitting the ground there. In parallel, we're also having some test projects for the transmission level, so the highest level of the grid. So obviously here, the criticality, the sensitivity, I would say, to the new technologies is much higher, hence those longer cycles. But what we are doing typically with the French transmission utility named RTE is doing tests in their own testing facilities, which are emulating the complete behavior of a substation in the field and replicating, in fact, the whole behavior of an existing substation in the field. So we've done some lab testings there, but which are very, very close to real conditions to be able to prove the reliability of the scheme, the performance, because we are adding more layers. So you want to make sure that at the microsecond level for the acquisition up to the millisecond level for production and control schemes, we are able to match the performance or maintain a level which enables to comply with the required speed in those type of substations. So we do have indeed a number of things moving in parallel. And I'd mention a third one, which is actually outside of the utility world, because I think we have also customers like data centers who are probably more familiar with this virtualization topics. Their whole IT infrastructure is running like this, so they are very familiar and with that and more open to make quick changes there. So we are seeing a speed in those environments of the testing and deployment that is increasing there. So it's still early phase, early deployment, few things into the field more as pilots and tests than anything else at the moment. No deployment at scale as of today, but we're seeing that in the next couple of years we start seeing some scale up for sure.
So what's that message to utilities then as you're piloting these projects? And you say that we might be a few years away from some wide scale adoption. They're likely to raise some concerns around cybersecurity, and anytime you make more of your infrastructure digital, that's going to be something that comes up, is how are you going to protect that asset? How are you going to make sure that it integrates with everything else? How are you thinking about some of those concerns? Because you know how it goes. You've done this before. Every time we have a new piece of technology that we're trying to get into the field, you really have to tell that story. You have to justify it for the utility, especially here in the US, so that they can go justify it to their regulator and say, here's why I need this. And then 5-10 years down the road, you have regulators dictating to utilities to go out and get an ADMS or a DERMS, because now we've understood that story and we don't even need you to convince us. We're going to tell you to do it. So how do we get to that stage? And what, if any, efforts are happening within the industry to kind of coalesce around that mission of we need virtual substations and digital substations so that can be the building block to that next level of innovation and resiliency and reliability, which we're certainly all in pursuit of?
Yeah, actually, there are great collaboration efforts from that perspective, which is quite unique, I would say, and that's part of the change that I've seen, to our earlier discussion, in seeing really the whole industry getting together, seeing the huge potential of this technology, but really getting together to make sure that the adoption actually cycle can be reduced compared to what we've seen in the past for new technologies. So typically in the US, we have a VPAC alliance for virtualized production automation and control, which Schneider Electric is participating to with many of our peers, many utilities themselves participating, IT companies, on the software side, on the hardware side. So everybody with obviously interest in that, but a very good collaborative spirit to define together, with all the actors of the industry, how to speed up the adoption, because the benefits are obvious to everybody, including the utilities. So a lot of reflection in this VPAC alliance, very good progress actually towards defining a framework that will help with interoperability, a proper definition of things. There is also, a whole stream just about education, so that, we can spread that, those concepts, explain how they work, show how, we can make it reliable, cyber secure, and so on, so that, all those things are covered because they are real concerns and need to be addressed. So yeah, I'm really happy to see the pace at which this industry group is progressing, and I think is really laying out the foundations for what will be in your future standards, probably future regulations, at a pretty high pace and in a very highly collaborative spirit.
So help dumb down that story for me, because I'm not an engineer. I talk to a lot of them, so I can usually play ball in these environments, but when we're talking about the value proposition, so digital substation, virtual substation, like the why, I think we've talked a lot about that, what you can get out of it. So then in a practical sense, can you provide any color around, once we get through testing and piloting, ideally at some point to scale in the next few years, what kind of headroom are we looking at on costs between, a standard substation versus one that is equipped as a virtual substation and has that intelligence and, technology baked in? Like, what's that kind of spread looking like? And then what is the back end return on investment for a utility when they do go to their regulator and say, the regulator is going to want to know what does it mean for safety and SAIDI and what other acronyms they're going to use to quantify and monitor their reliability and resilience. So I feel like putting it in at least some plain terms makes it a little bit more tangible.
Yeah. So first of all, I think the cost differential. So yes, the virtualization will come with some slight extra cost, maybe in the technology itself. For sure, there will be a slight difference, but it's really meaningless compared to the overall investment being made. So it's I think it's first a very slight difference, but the payback is huge, especially I would say in two things. One, which is the acceleration, in fact, of all the design, planning, design, and then implementation phase. That's a massive acceleration you can achieve. It's acceleration and it's de-risking, right? As I mentioned before. So, the ability to go and implement new things, new changes, new schemes will be greatly facilitated, accelerated, and reduced in terms of cost. So any kind of project cost for any evolution of the grid will be highly impacted there. So it's about, labor cost to do things in the right way and still deliver the right, operating thing in the field. And then it will be really, I think, the biggest, and we are, actually working to quantify all of that, but the biggest bang for the buck will really be in the upgrades. Because you need to be able to change the scheme of automation and protection of substations more and more frequently. Today, it's just impossible for utilities. When you have a fleet of thousands or 10,000 of substations, the reality that most of our customers, if they can touch a couple of % of their substation every year to do an upgrade, it's already good. What will enable is to do, massive changes of the schemes and evolve, wherever you have changes in the power flows of the grid because of the evolutions. Doing the changes will be much faster and much cheaper. again, every time you can avoid the truck roll, it's big money that is avoided, right? And it also indirectly comes back to the labor shortage issue. Because
it totally does.
One of the main limitations is also just having enough people to send to the fields to make those upgrades of the required protection, or put a bit more automation to make the grid smarter.
Yeah, and the thing with truck rolls too, yes, it's expensive because you need to send people out there, but not only can utilities not find enough people to get in the trucks, they can't even get the trucks. There are supply chain issues around trucks. So I mean, likewise. Again, tongue in cheek, but like that is the reality that utilities are facing right now. And we called out California utilities. I mean, their trucks now have to be electric. So I mean, they're facing like 4 or 5 year lead times, if not more, to get new field equipment. And that again, kind of layers the cake around the advantages here. And you touched on it there for a second about, say you're a utility with 1,000 substations. Again, PG&E is a good example here. We're talking a lot about the virtual substation in isolation. So what can that substation do? But when you've got 1,000 of them at scale that are virtual, that are communicating, and that are not only processing information on site, but sending that back to a central repository, what's the opportunity there when you do have that broad visibility, when you've evolved at kind of all corners of your footprint to the point where you have this constant communication and your forecasts are much closer to reality? What's the advantage for a utility once they go down that road and really commit?
Yeah, I think it's once it's virtual, you're really managing it as a fleet, and that's a major difference, right? It's not anymore point-to-point substation by substation management. You have centralized tools to deploy and manage your applications. So I'll take the example of fire detection on the lines and fire protection, which is obviously a more and more important and tragic topic. As of today, implementing the new algorithm that is able to sense properly that, there is probably a branch that is, touching a line regularly and that, may catch fire. Those kind of algorithms are not deployable in the field today. Okay, if you wanted to protect a couple of lines, the next year you have a scheme to go to those couple of lines, but, you'll touch, 0.1% of the grid every year. That's the reality of today. With a fleet of virtualized substation, that implementation has that brand new algorithms that is able to do some early detection and shut down the power before it has become a wildfire, would be done within a day. That's it.
Yeah, and I think about just so many pieces of operating the grid that go from, we're trying to get as accurate a forecast as we possibly can. But once we have real-time visibility at all these different endpoints, then your forecast, it'll still play a role, but it becomes less important because you know what's going on. Like you're not guessing what's happening on the system. And I think to a significant degree, we do have to guess about the impacts at various points.
Yeah, and I will insist on I think a second thing, which is really bringing the intelligence at the lowest level, in fact, of the grid. So the low voltage management, because the reality there is more and more distribution, right, of the generation and the loads and the variable loads. So as of today, nobody is really managing the low voltage grid, right? It's just a consumer, not predictable. You will control nothing on that side, right? And then you try to make sure the upper part of the grid is able to deal with that as a bunch of black boxes connected to the grid. Tomorrow, with virtualized substation, you can deploy optimization scheme at that low voltage level. So you'll put the measurements in place when you go to the substation. You need metering. You need to sense what's happening there. You can implement control points and manage configuration of your low voltage networks. You can also deploy optimization algorithms so that you can maximize the exchange of energy at the low voltage level. So it's transparent to the grid that is higher up, because you've already optimized locally. You can create community type of energy exchanges between all the consumers and prosumers which are connected to the same substation at the low voltage level. And that this optimization will need to evolve over time, and needs to nothing's perfect from day one, so you need to upgrade regularly. So having this fleet, you can deploy those schemes from that central location, upgrade regularly as you get smarter and smarter. So here the grid gets really smart, because you're not depending, in fact, anymore on a grid operator to solve this problem. It's happening directly at the substation level with artificial intelligence that you're able to deploy centrally and remotely to masses of fleets of substations.
Arnaud, I know you travel the world really beating this drum and sharing the story and kind of vision for the virtual substation and where utilities are going. We've talked about it now for about 50 minutes, so I'm going to give you the opportunity to give that. What is that elevator pitch on the urgency around making this transition? Why is it critical to utilities to digitize at the substation level as part of this smart grid approach? Instead of this just being a nice to have? Like what is that the best selling point that you've said, seen, heard around, like, we need to take this seriously and start making these moves?
Well, it's very clearly time acceleration of the energy transition. Nothing else. We know that the only way, we are on a trajectory at the plant level, which is really, really bad. We are not hitting at all, the targets that we need to, keep the warming controlled. This is absolutely needed to enable more electrification, and more electrification is the way to decarbonize. So the grids have to move much faster to handle that variability, these extra loads, in a smart way, to be able to address this challenge. To me, there is nothing else. That's the most important.
Thanks again to Arnaud Cantin for joining the podcast. Make sure to check out the all-new FactorThis.com for the latest news, commentary, and technical analysis on renewable energy and the power grid. And don't forget to subscribe to this podcast and our free newsletters. Thanks for listening, and we'll see you next time on Factor This.